Chapter 7 focuses on substitution and elimination reactions. Let's separate these based on what we've glossed over by not covering Chapter 6. Most of the reactions that you'll see in this textbook are heterolytic in nature, meaning that we cleave a bond giving 2 electrons to one atom and no electron to another. This is different than what you're going to see in Chapter 10, where you have homolytic cleavage, meaning that each atom gets 1 electron each. Most of the rest of of Organic 2 is going to involve these 2 types of reactions, heavily based on homolytic cleavage, except for paracyclic reactions, which will be an exception in Chapter 16. Now to Chapter 7. Here we're comparing substitution reactions, and we've got 4 main mechanisms to learn. The first one is SN2, which is one in which a nucleophile attacks an electrophilic carbon that contains a leaving group. And you want this leaving group to be something that wants electrons. This has got to be an electron lover, and because it's going to leave and be stabilized, usually as a negative charge, although there are exceptions. And then that nucleophile takes its place, forming a new bond to the carbon of interest. An example is shown here where we have sodium bromide attacked by sodium cyanide. Whenever you see a sodium, you can cross out the sodium, give a negative charge to what's left, and a lone pair. And then that's what's going to be used to attack that electrophilic carbon atom and knock off the bromine as the leaving group. It's important to note that inversion of stereochemistry occurs when you're dealing with SN2 reactions. So when you're crossing off that sodium, putting the negative charge on carbon, and you have the carbon coming in, see how the deuterium changes from a wedge to a dash to denote that change in substitution. If you found that part confusing, or if you still don't understand it, go back to Chapter 7 and look at the inversion of stereochemistry section that will guide you through why inversion of stereochemistry happens. The rate of substitution reactions, it increases with decreasing substitution around the electrophilic carbon. So the more naked the carbon is, the more likely it's going to undergo an SN2 reaction. The reaction increases with better nucleophiles, and it increases with polar aprotic solvents. What are these polar aprotic solvents? These are things like DMSO, DMF, oops, that was drawn wrong. Let's see. There. Needs an extra carbon. DMF. THF is a great solvent. Ethers as well. We want things that have polar bonds as part of their makeup, but we don't want them to be protic, meaning we don't want them to have an acidic proton. The SN2 reaction involves a single transition state. There are no intermediates unless a proton transfer is involved, but that's not actually part of the SN2 reaction. That would be a proton transfer that follows the SN2 reaction itself. But this lack of intermediate and only undergoing a transition state is what involves that inversion of stereochemistry to occur, as opposed to a racemization of stereochemistry. The more crowded substrates are and the nucleophiles and bases are, the more likely a reaction will go E2. So what is an E2 reaction? Here's one where we're going from an alkyl halide or other group with a good leaving group, and let's cross off that oxygen again and give or the potassium and give oxygen a negative charge. Here we're looking for a beta hydrogen atom, and that undergoes a 3-step mechanism to form an alkyl halide plus hydrobromic error plus water and plus Br minus. You can only go E2 when you have substrates that are too crowded for SN2 if the base is not bulky. SN2 reactions prefer less substituted alkyl halides, less bulky bases, and good nucleophiles, whereas E2 reactions prefer more substituted alkyl halides, bulky bases, and poor nucleophiles. In E2 reactions, often multiple products can form. For example, let's take the following substrate. 3 different reactions can form, 3 different products can form by treating this alkyl halide with bases that are bulky and not bulky. Let me fix an error here. That's supposed to be a carbon atom, not an oxygen. Actually, there are 2 different products that can form. We have what's called the Zaitsev product, and that product is formed by taking one of these blue protons, so I'll say that that goes with this bond, as opposed to the Hofmann product, which would take one of these green protons and form a pi bond there. And whether we form the Zaitsev or the Hofmann product is based on how bulky that base is. If the base is small enough, it can get into the bulkier part of the molecule and form the more stable alkene. Whereas if the base is too bulky, then it forms the more sterically hindered alkene, which is less stable. Bulky bases favor Zaitsev products. Here are some examples of bulky bases. You should be familiar with their names, you should be familiar with their abbreviations, and importantly with their structures. So we've got potassium terbutoxide, diisopropylamine, triethylamine, and then DBN and DBU. And what I remember about DBN and DBU is that they've got a 6-membered ring in both cases. This should be a 6-membered ring. And then they have either a 7 or a 5-membered ring to go along with that. Think about which one of those nitrogens is actually serving as the base there. When we consider the lone pair on the blue nitrogens versus the yellow nitrogens, notice that the yellow nitrogens have sp2 hybridized orbitals, whereas the blue nitrogens have sp3 hybridized orbitals. So actually it's going to be those ones with the sp3 hybridized orbitals that are more basic. We need an anti-periplanar geometry for E2 to occur. So in the first example, I've shown you an example of E2 occurring between these 2 blue carbons. And in this case, it doesn't matter which ones I've chosen for orienting the starting material, because the product will be the same in both cases because we have 4 methyl groups that are the same. But let's say that we have an E2 reaction that involves these 2 carbons. This would be one in which we had a non-bulky base because we want to get to that product that's less substituted. And for us to get there, we only form this product where the phenyl groups are cis. We can look at a Newman projection of this molecule in which the hydrogen and bromine are antiperiplanar, and see the reaction of these two groups collapsing on each other. So the green groups are on one side, the yellow groups are on the other side. That's what gives them their positions in the product. This can be tricky when we're looking at systems like rings. We have to keep in mind that when we have a substituted cycloalkane, for example, that we can only undergo E2 elimination from antiperiplanar hydrogens. So in this case, we have two hydrogen atoms that are antiperiplanar to the chlorine. And that's when the chlorine is in the axial position. But when it's in the antiperiplanar position, there aren't any hydrogens that are, when it is in the equatorial position, there are not any hydrogens antiperiplanar. So this one cannot undergo E2 elimination. So for this molecule, it's not relevant because all you need to do is have the chlorine in the axial position. But let's think about these two molecules and their relative rates of E2 reaction. Let's consider redrawing this first molecule, and what we want to do is remember that the bulky group needs to be in the equatorial position. So we're going to put that tert-butyl group up on an equatorial position. And because we've made it up on a down carbon, we need to put the chlorine on an up position. So we're going to put it here. Whereas in the conformation on the right, we're going to put that T-butyl group up, and that makes our chlorine with a dash go down. And what I think you can see is that we now have two equatorial hydrogens available for the first molecule, whereas the second molecule doesn't have any. Did I say equatorial? I meant axial. We have two axial protons here that can undergo E2 elimination, whereas on the right we don't have any antiperiplanar positions, because even though we've got hydrogens at the axial position, they're not antiperiplanar to chlorine. So this means that because molecule 1 spends more time in a conformation that can lead to E2, the reaction rate will be faster. There are some cases in which E2 cannot happen. So here I've shown a reaction which, if you didn't take into account the antiperiplanar requirement for an E2 reaction to occur, you might draw all three of these products forming. We've got two elimination products and one substitution product. But what we can tell about this molecule is that for the chlorine to be in the axial position, which is needed for the antiperiplanar arrangement, we have methyl groups also in axial positions. That means there are only hydrogen atoms in the equatorial positions, which does not allow for this antiperiplanar that we need. Our antiperiplanar arrangement is going to methyl groups. So this compound cannot undergo elimination at either of those positions. So these two elimination products do not form, And even though this is a secondary carbon with potassium hydroxide, and you'd expect substitution not to be as favored, it is the only product that can form. What often gets students tied up in this chapter is that there's more than one kind of substitution and there's more than one kind of elimination reaction that can occur, and these are our unimolecular reactions. These are far less useful reactions, the yields are lower, the reactions are slower, and they're subject to rearrangement, which makes their product distribution in some cases wider. The first step of a unimolecular reaction is for a leaving group to depart. I should say that's the first step, unless you have something like hydroxide as a leaving group, which you must first protonate with an acid so that water is a leaving group. I'll just put that as an aside. Otherwise, you've got your halide leaving as the first step, and you always get the formation of a carbocation. In a second step, a nucleophile attacks. In this case, I've used ethanol, and you get to this protonated intermediate. For it to become neutral, you then need to take away a proton with another molecule of ethanol that you can assume is in excess, and that forms the protonated ethanol and your neutral product. So this is an example of an SN1 reaction because what we've done is substituted the iodine for this ethoxy group. Alternatively, you can have the iodide leave, then instead of undergoing substitution, you can have your molecule of ethanol remove a proton from the carbocation and form an alkene. And now we have a protonated ethanol, and our green carbon-hydrogen bond here is now a pi bond there. These two reactions compete. It's difficult to separate these products, and it's difficult to control which one forms, which is what makes the SN1 and E1 reactions less useful to chemists. A further complication of SN1 and E1 reactions is carbocation rearrangement. Think about the transformation of this alkyl bromide into this alcohol. How would you do it? Well, if you use sodium hydroxide, you would compete with an SN2 reaction, although the SN2 reaction would dominate here. So you'd have this product, I should say it competes with E2. You'd have also the formation of this product plus this product. Also, if you use water and heat, then you have SN1 and E1 outcomes, but you also further have rearrangement, and let me show you how that works. First, your alkyl halide undergoes a leaving group removal, so you're making bromide minus, and then you have this formation of a secondary alkyl halide. And whenever you see the formation of a secondary alkyl halide a secondary carbocation, you have the formation of a secondary carbocation, you need to be concerned about rearrangement. In this case, what happens is that you have a hydrogen, a proton, and it migrates over because that can happen when you've got neighboring protons. And that proton is now over here on the adjacent carbon, which gives this carbon a positive charge. What that means is that when you have, we're going to assume that the conditions are water and heat. And what this means is that water can serve as a nucleophile and come in, and after deprotonation step you get this product that was not the one you wanted. And you can also get elimination from those two products to get these two alkenes, which are actually, in one case, is a different alkene than the one that we started with. Let's see, so this one is unique. So this is a difficult transformation to consider, and there's not a great way of going about ensuring that you have the product distribution that you want, at least not within a one-step reaction. Tables to know. Figure 7.9 on page 378 is an important figure, and I've copied it below. You need to know the categories of strong bases, strong nucleophiles, weak bases, weak nucleophiles. Most of the compounds that you need to know are here. You need to know their names, you need to know their chemical structures. What is DBU? What is DBN, for example? Not everything is listed here. We've left out triethylamine, for example. You also need to know this table. It's in figure 7.20 on page 319, and that is predicting the outcome between SN and E reactions. And this gives you a summary of whether you have a strong or weak base, a strong or a weak nucleophile, and then the nature of your substrate, whether it's primary, secondary, or tertiary. It doesn't list methyl halides as a substituent because all methyl halides can do is undergo substitution. Okay, so for our last topic, I'm going to ask you, what would happen if you wanted to replace an alcohol with a nucleophile or other group? You cannot simply use an alcohol and make hydroxide a good leaving group because hydroxide is a poor leaving group. What would happen if you introduced a base to this molecule? It would simply be deprotonated. So what you have to do is transform the alcohol into another group that contains a good leaving group, and we're going to do this with tosyl chloride and pyridine as a base. So what we'll do is say, let's take these lone pairs on the oxygen. They're going to attack the sulfur atom, and then that's going to displace a chlorine. And now we have this wonderful tosyl group attached to our alcohol. And what does that remind you of, the structure of? That should remind you of the conjugate base of sulfuric acid. The structures are almost the same. And what that tells you is that this tosylate, or OTS minus, is a good leaving group. Then we can treat this tosylate with sodium cyanide. The sodium cyanide comes in and attacks our alcohol. Let me do that with a different color to help avoid confusion. And let's put a plus on the sodium and a minus on the carbon. So there we get our SN2 attack. And it's important to notice where inversion occurs. The inversion did not occur here. We still have a wedge because we have not done a nucleophilic attack at that carbon. The inversion happens at the second step. We can turn alcohols into other things. For example, we can make an ether. We can take a base like sodium amide. That's 2 lone pairs on that nitrogen. deprotonate that alcohol to make the alkoxide, and then we can take a simple alkyl halide such as methyl bromide and convert that alkoxide into a ether and have bromide as a leaving group. For completeness, we should probably show that we're forming ammonia in that first step. So as I summarize this chapter, what I'd really like to encourage you to do is read the synthetic strategies, which is section 7.13 in your book, and that's really going to help you sum up the reactions that are in that book. And if you see that you're getting problems right, then go ahead and move on. And if you see that this section is a struggle for you, then go back and reread chapter 7 to make sure that you understand it, because the basis for chapter 7 and 8 and 9, those are really going to come back in Organic 2, so you'll be revisiting these same reactions as you discuss synthetic strategies.